Today I'm going to talk about differentially oblivious algorithms. To start, I'd like you to imagine the following scenario. There are a set of hospitals, and they each have a database of patient records. Now they would like to jointly perform a data analytics study on top of these, the union of the data sets. Of course, these patient records are highly privacy sensitive, so they would like to do this clinical study in a way that protects individual privacy. And how can you do this? Here's an idea. You can encrypt your database, and you can send it to a cloud provider like Amazon EC2. OK, so now we have this big database that sits in encrypted format on the cloud. But this doesn't give you computation yet, right? You have to be able to compute on the data. Let's now imagine the cloud has a secure processor, for instance, Intel SGX. For the time being, imagine SGX has not been broken yet. OK, now the data is encrypted in a way such that only the secure processor can decrypt it. Of course, the CPU has to decrypt the data in order to do computation. But as soon as any data leaves the CPU boundary, it'll be encrypted again, right? And in this case, assuming that the adversary cannot hack into the CPU itself, then the only thing the adversary sees is encrypted data. It does not see any clear text data. And this seems like a very nice idea. Not only can the hospitals outsource the computation, the adversary also cannot see the secret data contents. But as we all know, encryption alone isn't sufficient for guaranteeing privacy. And in this case, the CPU would have to access the data during the computation, and access patterns to even encrypted data can leak very sensitive information. And this is a well-known fact. There have been many attacks that exploit access pattern leakage. And here is a more recent attack. This was a paper that appeared in Oakland 2015. And now this group of researchers, they consider the following scenario. There is an Intel SGX processor, and this processor is doing a JPEG compression computation inside a secure enclave. OK, now they show if you only observe the access patterns, you can sort of just reconstruct the secret image that resides inside the enclave. And what's more cool about this attack is that they don't even have to exploit fine-grained access patterns. The only thing they're seeing is like the number of page faults that you incur, like over any duration of time. OK. Now, access pattern leakage is actually a common problem. It doesn't show up just in client-server scenario. Here's another scenario, right? So now imagine instead of outsourcing the computation to a cloud, these hospitals decide to jointly run a distributed protocol to do this clinical study. And earlier, we talked about encrypted data and secure processor. But here, imagine the data is secret shared among other hospitals, such that any individual hospital sees random data. And only when you combine the information at all of these hospitals can you make sense out of the data. So now, for implementing this trusted CPU, abstractly, we can think of running an MPC protocol. And this MPC protocol, in some sense, realizes this trusted CPU. And the same problem exists here. Now, this abstract CPU also has to access the data during the computation, and the same access pattern leakage applies. So in summary, basically, access pattern leakage is a common problem that arises in different settings. And of course, the important question is how can we defeat access pattern leakage, right? Well, about 2.5 decades ago, two great researchers, Ostrovsky and Goldrick and Ostrovsky, they proposed this amazing primitive called oblivious RAM, or ORAM for short. Now, what's ORAM? ORAM is an algorithmic approach that provably obfuscates memory access patterns. And the kind of security that ORAM aims to achieve is the following. An algorithm is said to be oblivious if, roughly speaking, its access patterns are indistinguishable from those generated by a simulator who does not know the input database. And if this is the case, roughly speaking, this real-world memory access patterns, they shouldn't encode any information about the private data set. Okay, so now depending on whether this is like, indistinguishability is against computationally bounded adversary or unbounded adversary, we can define computational or statistical security respectively. So this defines what it means for an algorithm to be oblivious. And I haven't said what ORAM is. ORAM is basically a technique for taking any generic program and compiling it to an oblivious counterpart. And of course, we want such compilation to not have to blow up the performance too much. Okay, so this is kind of like a semi-formal definition, but the way I like to think about things is that ORAM allows you to encrypt the access patterns. The security here, the security we desire here, should be as strong as encryption. Okay, so now at first sight, this is very counterintuitive, right? We know that we can encrypt data that exists in the form of bit strings, but access patterns are like a side effect of a program's execution. How can you encrypt a side effect? And amazingly, these two people show that indeed you can. And the techniques you employ are kind of like the following. So first, you would have to randomly permute the data that reside in memory, such that the permutation is known only to the CPU, but not to the adversary. And second, you would have to periodically reshuffle the data around in memory as you access the data. And Godric and Ostrovsky show if you do these two things carefully, you can actually construct an algorithm that completely hides everything and not incurring too much overhead. So when I first saw these algorithms, I was completely blown away. This is completely counterintuitive. Of course, so ORAM is this very amazing building block. And ever since Godric and Ostrovsky, there has been a lot of progress in this area. If you look at the state of art in this area, recent works have shown that any program can be made oblivious with, roughly speaking, logarithmic to log squared overhead. And this means that the oblivious counterpart runs logarithmically or log squared times slower than the non-private baseline. Okay. And not only do we have these non-trivial asymptotics, in fact, these recent algorithms have become extremely simple, and they're so simple you can actually implement it in hardware. And this is what a group of researchers in MIT did. They basically taped out a real CPU chip, inside which there is an ORAM controller. So this is a picture of the chip, and this is the group celebrating when the chip came back from the factory. It took them, roughly speaking, on the order of 350K to tape out a chip like this. And when you send it to the factory, you have to wait for 6 months before it comes back. So that's why it deserves a big celebration. Okay. So although ORAM has had a lot of progress in terms of practical efficiency, many still kind of believe ORAM is not in its prime day. Right? These techniques are still have somewhat considerable costs. And in fact, some of this cost is inherent due to a well-known lower bound by Godric and Ostrovsky. And this lower bound was recently improved in this amazing paper by Larson and Nielsen. Okay. N is the total memory size. So Larson and Nielsen show that you can remove the Bose and Bing's assumption in Godric-Ostrovsky lower bound proof. You can also show it for computational security, whereas Godric-Ostrovsky's bound works only for statistical security. And in fact, the paper is quite short. It's very easy to read, and I strongly recommend reading it. It's a very elegant proof. And of course, they show it for online ORAM because of Monino and Elab BIOS. So the proof relies critically on online. Okay, so now some of this cost is inherent. In fact, if you want a generic ORAM compiler, you cannot avoid logarithmic overhead. So this is kind of the bad news. There are other things that are not so nice. And one of them is the following. This is kind of often unsaid in the literature. If you look at all these ORAM works, they make an implicit assumption that the runtime of the program is fixed and publicly known. It means if you feed the program with any inputs, it runs in the same amount of time. Right? So this assumption doesn't always hold. If this assumption holds, then you can have like logarithmic to log squared overhead. But when it doesn't hold, if you still want the yes. So on some inputs, it can run longer than others, right? So let's say if that's the case, you can basically distinguish the input by reading the runtime. And if this assumption doesn't hold, what do we do? If you still want the access pattern to hide the input, you would have to pad to the worst case execution time over all inputs. And this can incur as bad as linear overhead, right? For instance, imagine the program incurs constant time on some inputs and incurs linear time on other inputs. So this can be hugely expensive. Okay, to quickly summarize, although ORAN has had a lot of exciting progress, many would agree that it's not in its prime day yet. And therefore, a very good question to ask is whether we can relax this obliviousness notion. And if we were to do that, there are two important goals that we should have in mind. Number one, this relaxation should still provide meaningful privacy. And number two, if we were to relax the notion, of course, we should hope for performance improvement. Okay, so this is what the rest of the talk is going to be. And in particular, I'm going to talk about a very natural notion, which I will call differential obliviousness. And this is basically where differential privacy meets access pattern privacy. I'm going to apply the wonderful notion of differential privacy to access patterns. I'm going to define the notion formally for you. And here's the scenario we are going to consider. Imagine there's a database of user records. And we are going to run some algorithm on this database. If you want something concrete, you can think of the algorithm as a compaction algorithm or a sorting algorithm. OK. Now, when you execute the algorithm, the CPU has to access the memory. And it incurs some access patterns, and the adversary can observe the access patterns. The adversary cannot observe the data contents, but it can observe the access patterns. So in this picture, I show the locations that are accessed, but in fact, the adversary not only can observe the set of addresses accessed, it can also observe exactly in which CPU step which location is accessed. OK, so the algorithm in general can be randomized. And if that's the case, what the adversary observes is a distribution on the access patterns. OK. So now, let's consider two neighboring databases. These two databases are neighboring because they're almost identical except for one user record, right? So on the left-hand side, this differing record is shown in blue. And on the right-hand side, the differing record is shown in red. OK, so now I'm going to run the same algorithm on this neighboring database. And I incur another set of access patterns, basically the red distribution. Now, we say that the algorithm preserves differential obliviousness if these two, the blue access pattern, the blue distribution, is close to the red distribution. And this needs to hold for any two neighboring databases. OK, so to complete the definition, I have to explain what I mean by close in distribution. And this is defined in the same way as in differential privacy. In this equation, right, basically, we want to say, look at these two probabilities. The probability that the blue access patterns land in the set S versus the probability that the red access patterns land in any set S. And now these two probabilities can differ by, at most, a multiplicative e to the epsilon factor, but we also allow additive delta difference. Yes, Adam? Yes, so my talk is going to focus on the statistical notion, and the adversary is unbounded. OK. But it's a very good question, can we do better with the computational notion? And these, I don't know yet. Yes, please.
What do you mean by set? Is it like memory location?
Set is, let's say, you take any subset of access patterns that can be encountered during the program execution. OK. So this is the definition. It's pretty simple definition, huh?
Just to make sure, the differential privacy understood what utility was with respect to. Here you're
you're actually doing computation correctly. It's just that
Yeah.
you're doing the access pattern in a randomized fashion in order to compare two parts.
Yeah, so that's an excellent question. For now, let's assume we want perfect correctness. The algorithm gives you a correct answer with probability 1.
Because there's no reason for oblivious RAM not to.
Mm-hmm.
You can get that. It's just that you want it to be more efficient, but we're still in the polynomial world, right?
Right. So let's for now assume we want perfect correctness. Okay. So, well, if your algorithm satisfies this notion for any two neighboring databases, then we say that it satisfies epsilon delta differential obliviousness. Okay. So I've defined what epsilon delta differential obliviousness is, and I'm going to try to answer these 3 questions, right? So this is a new notion. The first thing to understand is what is being relaxed here in comparison with full obliviousness. And then the second obvious question is like we want to make sure this is still a meaningful notion. And then third, which is like the technically more exciting part, is whether we can overcome oblivious barriers with this new notion. So let's start with number 1. What exactly is being relaxed here? And it's important to understand this. Okay. So first, with differential obliviousness, we only require closeness for neighboring databases. And if these two databases are further apart, then we allow their access pattern distributions to be like further apart as well. So this is not the case in classical full obliviousness, right? In full obliviousness, we want closeness for any two input databases. Okay, so the second relaxation is with respect to this e to the epsilon factor, right? So here we are allowing a multiplicative loss, which is non-negligible. Whereas, in let's say, classical statistical obliviousness, we do not allow this e to the epsilon factor, but we allow delta to be some kind of negligible function. Any questions?
Yeah, I have a question. For differential privacy, it's clear that you can't achieve it for if you ask for negligible negligible probability of the adversary of violating the condition. But here, you could ask for even statistical distance to be close on any two neighboring data sets, right?
Mm-hmm.
It's not clear why you have the e to the epsilon factor to me versus just asking for on any two neighboring data sets which are close, you have negligible probability of distinguishing.
On any two databases that are close, you have negligible probability of distinguishing. I guess that is the same as classical obliviousness if your data set is polynomially long, right? You can flip them one by one and like do a union bound. And
What exactly is adjacent neighboring databases?
And so this is the same as in differential privacy. Two databases are neighboring if they differ in exactly one position, and everything else is the same. Like, okay, all right. Okay, so here's an implication of the relaxations. So recall that in full obliviousness, if the program doesn't have uniform execution time, you would have to pad it to the worst case. But here you don't have to. Like it would be okay as long as on neighboring databases, the program has roughly the same execution time. Okay. So now I'm going to try to answer the second question. It is important to make sure this new notion still provides meaningful privacy. Yes, Gilad? Huh?
If you have an online
Why do I need, if I have an online ORM, why do I need a bound on the running time? That's a great question. I guess there are two ways to define ORM. One is like every time you make a logical access, you compile it into this oblivious form. But another definition is like if you think of it as a program and the program takes some input. And normally, if you're not worried about leaking execution time, you can take this online notion and just compile it into an oblivious form. But the oblivious form would leak the execution time. But if you really want to satisfy this notion that I mentioned, right? You want the access patterns to not leak anything about the program's input, then not only do you have to do that, you also have to pad it to the worst case execution time.
Quick question. So following up on Gilad, suppose you do this online thing, would it automatically satisfy your definition at least?
And if you also pad it to the maximum,
Not pad it to the maximum.
if you don't pad it to the maximum, it doesn't necessarily satisfy because the length of the termination channel, in programming language it's called the termination channel, but it's basically the length of the execution can leak something about the inputs.
Right, but here you're assuming neighboring databases are going to be close anyways, so leaking this information might automatically satisfy your definition.
I guess I'm kind of saying like if your mechanism, if you design like a randomized algorithm that guarantees closeness of execution time for neighboring inputs, then it would be fine.
Like with some noise or something, in what you're saying, right?
Right. So like I think if your original program has this property that for neighboring inputs, the running time is close, then you don't have to add a lot of noise to the running time. But if your original program has the property that for neighboring inputs, it can vary vastly, that means like the global sensitivity is very high for the running time. So you have to add a lot of noise to get that. I couldn't hear what you were saying. Leo?
So you only talked about the total running time. What about the inter-access time? Because you can't assume that memory accesses are always time.
Yeah, that is a great question. So I don't have a good answer for this in this talk. I'm going to assume all the, or maybe this, if the access time is data independent. So this is related to the question like where the cache sits. Like if the cache sits after the ORAM, then it would be fine. But if the cache sits before the ORAM, there can be side channel leakage. I'm not sure if that's confusing or not. Like,
It's not just the cache. I mean, sometimes you will be able to, depending on the value in your registry, you may be able to do more or less computations before you have to go back to that.
right, so partly why these memory accesses have different times is because sometimes there's a cache, right? So if you compile it with an ORAM compiler first, and then it hits the cache, then it's already random, so it doesn't matter. Like it actually, this approach actually secures against cache timing attack by making going through ORAM first and then hitting cache.
Not cache time, speed time. If the value is 0, then cycle the CPU for a long time with lots of noise.
Well,
we
we're assuming all the data is randomly encrypted, so you cannot actually see it whether it's 0 or 1. All right. Okay. Okay, so does this still give meaningful notion of privacy? Well, I guess this is a relaxation, right? So it varies from application to application. For example, if you're trying to protect your secret encryption key that's securing your 10,000 bitcoins, probably you don't want to apply this notion. It's too weak. But there are scenarios where this notion does make a lot of sense. So DO stands for differential obliviousness, right? So recall in the hospital application I mentioned earlier, the whole intention of this clinical study is to release some useful statistic to the public. Like, if you don't do that, you don't have any utility, and that kind of defeats the whole purpose of doing this. So now, if your intention is to do this anyway, like I want to reveal differentially private useful statistics to the public, and this would argue, no matter which approach, whether you're outsourcing it to a cloud or doing it in a distributed fashion, like you may be able to say that any statistic that is differentially private is OK to release. OK, so in these scenarios, it kind of makes sense. OK, so before I talk about our algorithms and lower bounds, I want to kind of revisit how to set these parameters. Salil already mentioned this, right? So for epsilon, I'm going to assume it's some constant independent of n. Typically, we want epsilon to be like 0.1 or to 1. For delta, I want it to be like a negligible function, because you should think of delta as the probability that some individual will fail to get privacy. For instance, if delta is like 1 over n, then in a database of size n, in expectation, one guy will fail to get privacy. And in general, it's a good idea to set it to be a negligible function. I'm using n as the security parameter, but in general, this can be any generic security parameter. Okay, but in this talk, let's stick with n as the security parameter. Okay. So now is the more exciting technical question, like with this relaxation, can we overcome oblivious barriers? Okay, and excitingly, I'm going to give you an answer in the affirmative. And I'm going to use a very simple algorithmic task called stable compaction, which in a moment I will explain what it is. And for this algorithmic task, I'm going to show if you want for obliviousness, then a broad class of natural algorithms in the balls and beans model must incur at least n log n overhead. Whereas if you only need differential obliviousness, you can do n log n. So for our upper bounds, like I said, we are going to use epsilon constant and delta negligible function in n. So this shows a separation between these two notions. Yes, please. Sorry, could you repeat the question? That's a very good question. So we haven't tried implementing it yet. I think there's a lot of optimizations you can do when you actually implement it. And it also depends on, I guess, like the degree of security you want. So practical performance is like a very exciting future direction, which I will mention also at the end of the talk. Okay. So here's what stable compaction is. Imagine your input is a memory array, and some of these cells store CryptoKitties. Okay, and other cells are empty. So does anyone know not know what CryptoKitties are? Okay, so CryptoKitties, they are kind of these non-fungible tokens on Ethereum. You can breed them, and some of the rare breeds sell for like 100K USD. So this is kind of like a game on top of blockchains. In fact, when Ron and Shafi sent me email about this workshop, I swear I was the #1 to reply because I thought now this is my opportunity not to have to give a blockchain talk. But here, this is like the blockchain part of my talk, CryptoKitties. Okay. So what do you want to do here? The kitties are what I want. So I want to compact the kitties and start them at the beginning of the array. And then the remaining cells would be left empty. And not only do I want to do that, I want to preserve the order, which is what stable means. So I want to preserve the order in which they appear in the input. Okay. So very simple task. And of course, the first question to ask is, why do we care about this? There are a few answers. First, this is about the simplest and yet non-trivial example I can find to show you a separation. Second, it turns out that compaction is a very frequent building block in the design of ORAN and oblivious algorithms. So you would hope that maybe this could be a useful building block in designing differentially oblivious algorithms too. And indeed, this is the case because in our paper, this is actually kind of like a warm-up scheme. And we use these techniques to design more interesting things like merging algorithms and range query data structures later. Okay. So obviously, in the clear text, the task is very easy. Like you would linearly scan through the input. Whenever you encounter, Cupid kitty, you write it down in the output array. You move your pointer forward. Encounter birdie kitty, write it down. Move forward, empty, don't do anything. Move forward, ninja kitty, write it down, and so on and so forth. So as you can see, this will complete in linear amount of time. But the algorithm is not secure because it leaks the exact progress. Right? You leak the position of the pointers, and that will tell you exactly which positions in the input array contain kitties and which positions are empty. Okay. Yes, please.
So what is is there a public output to this algorithm? Do we worry about that, or?
So maybe I think a better example is like if you run some differential, let's say imagine I want to run some data analytics task on this data set. And in the end, I might want to reveal some differentially private statistics. So here we actually have differential privacy, and the statistic released is also differentially private, and you can apply the DP composition theorem.
The statistic is the access pattern, or
the access pattern, like I guess it's kind of a side effect, but in the end there may be some statistics, like aggregate statistics, maybe a K-means model, or is this drug effective? Like there's something, does smoking cause cancer? There's something you intend to reveal, and that statistic you want to publish is DP, and here the access patterns are DP. So in the end, like you lose basically the composition of. But the access patterns are not what you necessarily want to publish. Like it's kind of just some leakage, but it's DP leakage.
But I'm wondering about in the the output of the stable compaction, the compacted list. What's happening to that?
So this is kind of like you should think of it as like a building block in a larger algorithm. Maybe this is not like in practice you don't just want to do a compaction, like it doesn't give you any useful statistic to reveal, right?
I see.
But in terms of the problem, the output is the output. So you're not hiding the order of the thing. You just want to hide the spaces, the location of the spaces.
Yeah, all the data items are encrypted. So like the encryption already kind of hides the contents. And what remains to be hidden is like which locations are full and which are empty. Yes, Aniket? What is the input database here? The input database, let's imagine it's like every kitty contains a kitty record, like the age of the kitty, the special traits of the kitty. So I'm just abstractly denoting it as like one small memory cell, but it can carry like a record with it.
So
the kitties are the users, right?
not whether that's not because if you just kitties doesn't matter what those kitties are, I can run your algorithm whether that's a pink one or a blue one, the same access pattern, right?
That's a very good question. So I guess you should think of it like this is kind of like a building block in our full paper, because later we use it to construct like a range query data structure. And there this notion is more intuitive, like what it means to be the data set. So in the range query data set structure, you are inserting records into the database and you are making range queries. And there, basically, the neighboring database are defined on the user records. But then this algorithm makes use of this building block. So now every memory cell, like neighboring means two vectors that differ in exactly one position. Two memory vectors that differ in exactly one position. This actually gives point to a very good question of like composition. How many? 10 minutes. OK, so let me go over this. Yes.
Where did you find the pictures of all these different?
On Google. So let me kind of go over the algorithm. And I may not have time to go over the lower bound. So if you want to do it obliviously, it's very simple. You use a sorting network, like if you use AKS. This takes n log n time. And in fact, if you want full obliviousness, n log n is inherent. You can prove a lower bound. We did it in like one of our other papers. And this lower bound holds for a natural class of algorithms that are in the Bose and Bing's model. Basically, the algorithms, assuming the algorithm does not perform encoding on the kitties, and they only move the kitties around. OK. So I wanted to tell you how this lower bound works, but actually I think the upper bound is more exciting. I'm going to tell you how to do it with differentially obliviousness in n log n time. And the high-level intuition is, so if you want full obliviousness, you cannot leak progress at all. But if you only want differential obliviousness, right, you want closeness only for neighboring inputs, you actually can leak a rough notion of time, rough notion of progress, as long as this leakage is DP. So that's the thing that we are going to leverage to improve the running time. And here's how the algorithm works. OK, so I have my input memory array. I'm going to look at polylog size batch. For now, imagine there's an oracle, and the oracle gives you differentially private advice. And now, in this case, the oracle says that there are 2 to 5 kitties encountered so far in this blue box. So how can I make use of this advice? I'm going to take this batch, and I will apply oblivious sort to this tiny batch. And I get a sorted array where all the kitties appear in front, and all the empty cells are at the end. So now I take this sorted array, and I truncate it. I take the prefix of length 5, and I write it to the output. So maybe this is a bad example because there are only 5 things in the input. But in general, if the input is longer, you truncate it at 5 because this oracle tells you there are, with high probability, there are at most 5 kitties. OK. So now, given this oracle's advice, I know almost surely that the first 2 cells have been occupied. But for the remaining 3 cells, I'm not sure. They could be occupied. They could be empty. OK. So one thing I want to mention is even though I'm using the actual number 2 to 5, they're actually a polylog. So this differentially private estimate has polylog error. And you can be sure that this is a correct estimate except with negligible probability. OK. So this means the slack consisting of question marks is like polylog in len. So now I'm going to move on to the next batch. OK, because here I'm not sure if there are kitties or not, I'm going to take this blue box and that blue box. I'm going to combine them, and I will obliviously sort the union of the 2. And again, I want the kitties to appear in front and the empty cells to appear at the end. OK. Now, again, we ask the genie for advice. OK, we want to write the sorted result to the output array again, but we are going to ask the oracle for advice. And the oracle says, up to this red point, there are maybe only 5 to 8 kitties, except with negligible probability. So I know the first 5 cells have to be occupied, almost surely. And then the remaining 3, I'm, again, not so sure. So you basically do this algorithm until you reach the end of the array. OK. Now, as you can see, this algorithm takes n log n time. And the log n is coming from oblivious sorting on the polylog-sized segment. OK, any questions so far? So very simple algorithm. The algorithm is incomplete so far because I haven't told you how to realize this genie, right? And what we need here is an oblivious and differentially private algorithm that can estimate all prefix sums with polylog error. It turns out this is also a non-trivial building block. Well, in general, actually, we don't need oblivious. We only need differential obliviousness. But it turns out, for the building block we use, we can just achieve obliviousness fairly easily. So how do you do this prefix sum estimation? The challenge is that we need all prefix sums. And now the naive algorithm is to compute all of these n prefix sums and add independent Laplacian noise to each. But this is a very bad approach because your privacy will degrade linearly with respect to the number of queries. Another way to think about it is if I have constant epsilon budget up front, I have to split it into n portions and apply each portion to each query. So this will, in expectation, give me linear amount of error per query. And recall that I said we want polylog error instead of linear. So in this work, joined with Hubert Chen back in 2010, we have a different approach of doing this. And the idea is also very simple. We build a binary tree over the inputs. OK, now every node in the tree, you should think of it as representing a range, right? Like in this case, the red node represents this red range. And what I want to do is I want to compute the DP estimate for every node in the tree, indicating, roughly speaking, how many kitties are in the subtree. OK. And the nice thing here is that observe that every input location appears only in logarithmically many nodes. And this means if you have epsilon budget up front, you now only need to split it into log n portions. And then you can apply this log n portion to the small portion to each estimate. And this basically you can show in expectation like the error is like log n squared or something, but you can also show the error is like, with high probability, the error per node is like polylog. And now, every prefix sum can be expressed as logarithmically many nodes in the tree, right? So here, these two red nodes express this prefix sum. And therefore, for every prefix sum, I also achieve polylog error with high probability. OK. So we are going to run this algorithm. And another observation here is that this algorithm can be run in an oblivious manner. It's like naturally oblivious. You just basically compute all these estimates in the tree. Like you compute the prefix sum, exact prefix sum in the tree, and then you add noise to each node. OK. So basically, this is the algorithm. I guess the cool thing is that we have techniques that non-trivially combine DP techniques and oblivious algorithms. And this means two things. Number one, we are going to apply oblivious algorithms to small polylog size bins. So they incur only kind of log-log multiplicative overhead. And number two, we are going to run DP mechanisms, but we are going to run them in an oblivious manner. So these are the higher level insights we have. And here's kind of the theorem statement. We can achieve n log log n runtime. We get constant epsilon and negligibly small delta. OK. So maybe I will skip the lower bound proof. So we can show like with obliviousness, you really need n log n. But I want to mention something that's very surprising and counterintuitive. With this lower bound technique, not only can you prove oblivious lower bound, you can also show this non-zero delta is necessary. Right? Remember in our upper bound, we set the delta to be non-zero, but negligibly small in n. And in fact, this is necessary. And if you, in particular, if you want epsilon differential obliviousness with the zero delta, the same oblivious lower bound would apply. You would still need n log n time. And this is very surprising because this holds for any arbitrarily large epsilon. Like if your epsilon is really, really large, you have very little privacy left, and you still are subject to this lower bound. So this is like really surprising in some sense. I guess there's an explanation for this. But in some sense, what this is saying is that if you want to get these asymptotical gains, you have to either introduce additive privacy error, or you have to introduce correctness error. OK. OK, so like I think this may not make much sense without going over the lower bound. So let me now just conclude. I've talked about only like glimpse of our results. We have more fancy algorithms like merging and range query data structures in our paper, where we show some very similar results. Like we can achieve differential obliviousness with log-log and blow-up in comparison with non-private, whereas for obliviousness, you need log and blow-up, and that's necessary. OK. So merging is like a much more sophisticated algorithm. And the cool thing, I want to mention the cool thing is that it makes use of this really cool algorithm called differentially private interior point. And this is a paper by Mark Bounds, Leo, Kobe Nissim, and others. I really love this algorithm. OK. There are like a lot of interest in the community on differentially private access patterns. And there are a couple works that we inspired our papers. One is by Wag et al. And they look at differential privacy for ORAM. I guess their notion is kind of incomparable, and they only achieve constant gain. And our paper is also inspired by Claris et al. And they care about differential privacy for access patterns. But in comparison, they want differential privacy for the length, but otherwise they want full obliviousness. So the definition is also of a different nature. And you are going to hear Saha's talk tomorrow. OK, so this is just the beginning. There are many exciting questions. Like, how can we define this notion for generic programs? I've talked about specific algorithms that run on user records. Composition is a challenging problem, which is kind of arose in these questions you guys raised, right? Like, when you want to compose these algorithms sequentially, the previous algorithm's output is the next one's input. So now the notion of neighboring database will change when you do this composition. What are some of these alternative notions? that relax access pattern privacy. And I haven't talked about practical performance at all. So it would be great if these algorithms can give you a practical improvement over Oblivious as well. OK. All right. So I guess that's it. Thank you so much.